Hi everyone, so this is the last in a trilogy of videos on scattering from potential energy landscapes. So we looked at a potential step, and in the last video we looked at a potential barrier, and we talked about the case where the energy of the electrons was smaller than the height of the barrier, and we talked about tunneling. This video we're going to look at least initially, we're going to look at this case in terms of where the energy of the electrons is now greater than the height of the barrier. That's important when it comes to our wave function and our probability density, which look like this. And what's particularly important to note is that in region 2 now, if you go back to the last video, you might remember from the last video, in region 2, in the barrier region, when the energy of the electrons is less than the height of the barrier, what we end up with is the square root of a quantity that's negative. That brings in our imaginary number, which means that, as described in the last video, what happens is that we have exponentially decaying. It's a real exponent, which means that we have an exponentially decaying rather than an oscillatory wave function, and therefore also an exponentially decaying probability density in that region. When the energy of the electrons is greater than the potential barrier, like here, then what we have is positive kinetic energy again, and therefore we are back to the situation of having complex exponents, e to the I, let's put a wave number or spatial frequency in this region, let's label it as K2. We've e to the I K2x, and also because it's a barrier, which means we can scattered in the other direction, we've e to the minus I K2x. Okay, so I could take you through laboriously, like I did in the last video, take you laboriously through the algebra. I'm not going to do that. It's pointless. You know, work through that algebra yourself. It's really nothing beyond A level. And the transmission coefficient is given by this. If you look at that carefully, two important aspects. One that's perhaps obvious, one that's, I guess, much less obvious, or possibly much less obvious. First of all is that as we make E greater and greater and greater than V0 until E becomes very much greater than V0, so we reach the classical regime, then the transmission coefficient goes to 1, which is what we'd expect. When in the classical regime, when the energy is so much greater than the barrier height, then we are not going to expect any reflection at all. Secondly, and perhaps less obviously, so what we have in the denominator there is a term well, that's the width of the barrier, and that's our wave number in the barrier region, which is going to be given by square root of 2m E minus V naught. I'll do it like this, over h bar. So positive quantity. So an interesting question to ask ourselves is when this term might go to 0, because if you look at the expression of the transmission coefficient, which I'll put there, then if this goes to 0, our transmission coefficient goes to 1. And when will this go to 0? Well, it will go to 0 when this thing and if you remember all the way back from Newton to Einstein last year, then this is nothing less than the boundary conditions that we set up in the infinite potential well, whereby at the edges of the well, how many times you have to see this? 0 and A. What we have are boundary conditions that mean that the wave function goes to 0 at the edges of the well. And for that to happen, then what we must have is that the argument of our sine function is an integer number of multiples of pi. But what we've just seen is that if this condition is met in terms of the transmission coefficient for a potential barrier, then we get perfect transmission. Our transmission coefficient goes to 1, which means that we've got the same condition for the infinite potential well in terms of the energy eigenvalues of that well as we have for perfect transmission. And when we have this matching of energies, what we have is a resonance. Just like in classical physics, when, you know, we're oscillating something. Here's one I prepared earlier. This poor long suffering monkey spends an awful lot of time in the end of this bloody spring. So let's bouncing up and down. It's natural frequency. Fairly large response. So, let me change the frequency at which I'm driving this. I'm trying to keep the amplitude roughly constant while I do this. But you'll see that monkey here is not moving around anywhere near as much. Whereas if I go back to driving it at the resonant frequency, off he goes with a relatively large amplitude. So the response of the system depends on the matching of the driving frequency to the natural frequency of the system. And remember, in quantum mechanics, we've got a direct relationship between energy and frequency. So the co-opting of the term resonance is not that strange and is entirely valid. So when we match the energy of the incoming electrons to a particular energy level of the system, we get a large response. Hence, we get our transmission coefficient goes up to 1. You can also, and perhaps you'll look at this in wave phenomena, if you haven't already, also think of it in terms, interestingly, in terms of an impedance matching problem. It's not something I'm going to go into, but if you're interested in pursuing this idea more, I know it's not going to be examinable, you could think of this in terms of impedance matching in, for example, electrical circuits, but also in terms of acoustics and sound, and just how waves in general get reflected from or transmitted through different interfaces and different boundaries between materials. But we don't need to go that far. All we have here is the key idea. Think of the energy levels. I'll just put them in the well just like this. Now I'm just sketching the energy levels, and they go as n squared, as you know. So we'll do it like that. So we have particles incident from this side, traveling through. When the energy of those particles matches this level, or this level, or this level, we get resonant transmission. We get a transmission coefficient remarkably goes to 1. So resonance of this type is exceptionally important. Just like if we want to get as much coupling and transfer of energy between two systems in classical physics, we have to think about how to match the resonant frequencies. Here we have to think about matching those energies at the quantum level, just as we have here. So if we plot that out, if we take the expression of the transmission coefficient and plot it out as a function of E over V0, so the energy of the electrons above V0, here's what we get. And you can see those peaks clearly in the transmission coefficient, and it's going all the way to 1. As we match the condition for the energy levels of the infinite potential. Now, you might think, well, this is strange. Hang on, it's a finite barrier. Why are we using the infinite potential well? Well, the reason we're using the infinite potential well is because the condition for t equal to 1 in our expression for the transmission coefficient involves that sine term, and we just ended up with the same boundary conditions which set that term equal to 0 as we have in the case for the infinite potential well. And so it's a really nice, elegant solution that drops out directly from the mathematics. Also shown in the inset here to that graph is experimental STM data, where you can see these oscillations. So it's called a scanning tunneling microscope. Interestingly, in this particular case, it's not being used as a tunneling microscope. The energy of the electrons is greater than the barrier height. So we've set it up exactly, or they've set it up. This is data from quite some time ago, from 1993. And they've set the experiment up so that the energy of the electrons is greater than the barrier height. So exactly the same case as we've been discussing here. And you can see the oscillations quite clearly. There are two different graphs there. And this goes to show you one of the frustrations of scanning tunneling microscopes is that it's all dependent on the tip, and different tip states and different tip work functions, either the electronic structure or the atomic structure, and they tend to be coupled together. If that differs from day to day, if there's been a mild crash or a big crash of the tip, or something is absorbed on the tip during the night, or somehow the tip is changed, that can change the electronic properties of the tip, and that shifts your potentials around. And hence, you can see those oscillations, you can see them remarkably clearly, but it all depends in terms of the potential, the value of the potential that the electrons are seeing depends not just on the sample, but also on the tip. But putting that all to one side, those oscillations are incredibly clear, and it's exactly the same effect as pops out of, as you might hope, as pops out of the theory. Just ignore the sort of monotonically rising lines in that graph because they're just a map of what the position of the tip is as they're doing the experiment. You don't need to worry about that. But in terms of the comparison of the oscillations in the transmission coefficient, theoretically and experimentally, it's a pretty strong agreement, I think you'd agree. So that's in the case where the energy of the electrons is greater than the potential barrier height. Let's go back to tunneling, and let's go back to using the STM in its tunneling mode. This is phenomenal. So this was a paper published last year. I love this. It's, you know, we've spent so much time on particle in a box, and you're probably bored with particle in a box. I got a great email from one of you. I'll not mention his name, but it made me laugh. It says, I'd love to take that particle and throw it down a deep, deep, deep well. Brilliant. Absolutely brilliant. I understand, but the thing with the particle in a box is it captures so much of quantum mechanics. It really does. It's why we keep coming back to it time and time again. And at this point, if you are used to it to the point of absolute frustration, that's pretty helpful in terms of at least giving you, well, I'm used to this thing. Before we venture off into the unknown, if we connect the unknown to something I do know, it can be very helpful. So that's why it keeps popping up. And yet again, here it is. So what the researchers have done, and as I said, this paper was published last year, is manipulate individual indium atoms on an indium arsenide crystal. Don't worry about the details of the crystal other than the electrons at this particular surfaces, and this is certainly not true of all surfaces, in fact it's the exception rather than the rule, behave very, very much like free electrons. And I will come back to what I mean by that. And so if we're going to find good agreement with our particle in a box model, where we set up the potential as zero within that well, we need to find systems, material systems, where electrons behave like free electrons. And it might seem strange that we can take something which is an idealization and represent it in material systems, but we can. And this is the best example, at least I've found to date, of just this, the realization of the particle in the box. So you can see that the atoms, they formed a chain of 30 indium atoms. That acts as a container for the electrons. And look, it's the probability density. The STM is mapping out the probability, the textbook probability density, in terms of our ground state and all the various other states, all the various other excited states. But what we can do is actually go beyond the probability density, or what they've done is go beyond the probability density and also measure the energy levels associated with these states. So what they do is they vary the energy of the tunneling electrons, and they measure the tunnel current as they're varying that energy. Moreover, what they've done is very clever. They've moved the tip round back and forth to find a place where the probability density and hence the tunnel current will be maximized, so they get better signal to noise ratio. That's why you've got three separate colors in there, because they refer to different parts on the chain where they've moved the tip around to maximize their signals. Very clever. But leaving that to one side, you can just imagine all of these in the same color. Doesn't really matter. The key thing is to look at those peaks, and those peak positions follow what we'd expect in terms of this. I'll write it down. So what they see, the energy levels that they measure vary as n squared. So it's exactly what we'd expect for textbook for a particle in a box. One thing I should point out, but this is absolutely a tangential point, not examinable, but for those of you interested, although we can treat these as free electrons, there is a proviso, and it relates to just what we think of in terms of as the electron mass. You'll see a lot about this next year in solid state physics when you look at what's called the effective mass. Very much a side point, not examinable in the quantum world, but for those of you who are interested and think, well, how can we treat them like free electrons? There is a certain proviso there. So this would seem to provide us with good evidence that the electrons do indeed behave like free electrons. And that quantum corral image that I keep bringing up, it's exactly the same idea. The electrons at that particular surface, which is a copper surface, also behave as if they're free electrons, or silver surface also behave as if they're free electrons. However, as I say, it's the exception rather than the rule. So if we don't go about constructing these types of quantum well structure, how do we determine whether the electrons do behave like free electrons at a given surface? Well, it's all down to the beauty of Fourier mathematics again and Fourier analysis. There are different ways of doing this. Again, you'll see some of these in solid state next year. But for me, the most elegant way is that we translate from our position representation, which is our STM image. It's a real space position image. We're measuring the probability density as a function of X, as it were, real space. If we now take our image and Fourier transform it, what we get is a representation in terms of K, in terms of spatial frequency, aka wave number, aka wave vector, aka momentum space. So we can translate, just as we've done throughout the module, we can just take our image and translate it to momentum representation. Now, the big difference here, of course, is that it's a two-dimensional transformation rather than a one-dimensional transformation. Don't let that put you off. I'm not asking you, really not asking you to understand the minutiae of just how we go from a two-dimensional image and what its Fourier transform should look like. You'll see a little bit of this in wave phenomena. You'll see that in wave phenomena next semester. But just that idea of we can translate from position to momentum simply by taking a Fourier transform of our STM image is very, very powerful, because that allows us to access wave number. It allows us to access K from the image. And from that we can work out momenta, and from that we can also work out, do we have the right dispersion relationship for free electrons? And what's that dispersion relationship? Well, I've written this down a number of times before. E is equal to h bar squared k squared over 2m. Now there's nothing to that formula other than classical expression for momentum and de Broglie's relation, P is equal to h over lambda. Make sure you can take P is equal to h over lambda and P is equal to mv and get that. And that, once we have that relationship between the energy and the wave number, the spatial frequency of our electrons, which is parabolic, E goes as k squared, that's the characteristic signature of free electrons, that type of dispersion relation. And in some cases we're lucky enough in the big bad real world that we have samples and materials where we do have a free electron like dispersion like this, where the energy goes parabolically, goes as a square of the wave number of the spatial frequency. And here's a very good example on a silver surface where they've taken the STM image. You can see all the ripples, you can see all the scattering of the waves, the electron waves at that surface. Amazing image, amazing. And then they've taken the Fourier transform of that. Now, I'm not asking you to be able to visualize this directly as to how you go from here to here, but just note that what we have in momentum space is a relatively straightforward pattern, whereby we've got a ring, which means we've got a preferred wave number, we've got a preferred K. If you imagine tracing through that ring, cutting a profile through it. So these are our Kx values on this axis, sorry, and these are our Ky values. So all we've done is, you're used to thinking of momentum in terms of a 1D representation. Now we can reduce this to a 1D representation, just as we did in terms of that Fourier, F-U-R-R-I-E-R analysis interactive figure all the way back in video 7. I'll put the link down there to the interactive figure. Same idea. What we're doing is we're going to slice through this image and slice through this pattern and just take our 2D pattern and reduce it for one line to 1D. So if we were to slice through here, for example, what we'll see is, well, we'll have a peak over here and we'll have a peak over here. And they should be roughly the same size. So this, I'll mark it with a little star, corresponds to, well, positive, to that point. And this, I'll mark it with a negative, corresponds to that point. And then what you do is you're just stacking those up. And so what we have here is our Fourier transform again, as a function of K. That's our 2D representation. You're more used to looking at it in this case in terms of a 1D representation, but it's the same idea. Really do not worry about trying to get 2D versus 1D right in your head. The only important thing to realize from this is that it allows us to translate from position to momentum, to get those to get the wave number, the spatial frequency associated with the electrons. And if you now vary the energy of the electrons, and you can do that simply with the STM, simply by varying the voltage between the tip and the sample, then what you get is this. And you can see it's parabolic. If you can fit a curve that gives us that E is equal to h bar squared k squared over 2m. E is proportional to k squared. And so once you have that parabolic dispersion, as I said, it's a signature of free electrons. Okay, I really wanted over the last few videos to make the connection with the real experimental world. It's a little bit frustrating at times where some aspects of physics tend to forget that there's a big bad world out there and just get buried in the elegance of the mathematics. Remember, quantum mechanics is a theory all about observables. Observables are built into it in terms of how do we get our observables out of these mathematical objects. It's by definition about connecting with experiment, about connecting with observation, hence observable. And yet sometimes there's a little bit of, I don't know, how can I put it, arrogance in a position that states, well, unless the mathematics is extremely complicated and extremely difficult and extremely abstract, you can't be doing proper physics. I hate that attitude. I really hate that attitude, because what we should be doing is really not getting fixated on the most elegant maths. What we should always bear in mind is we have to connect with experiment. We're doing physics. We're not doing mathematics. We're not doing pure maths. We're doing physics. And we're using the mathematics as a tool and as a model. And that's essential, as a model to describe the real world. And sometimes, unfortunately, there's a great deal of confusion between what's the model and what's actually happening out there. For example, we model a world, the classical world, using vectors. It's not like if I look around this room, there's arrows pointing everywhere. So I'm putting these provisos in place because in the next few videos, we're going to jump into the matrix. We're going to jump into matrix mechanics and Dirac notation. Very mathematically abstract. I will do my best to connect it, obviously, with what you've done thus far and with the big bad world. But it is pretty mathematically abstract. I will see you in the next video for matrix mechanics and Dirac notation. See ya.